we are adding finally two drags to each other, and when the Mach number is increasing, this is increasing with Mach square, and this is increasing also. And when you are going supersonically, this is again increasing, and this is again increasing. So these two features, these two factors, can become really detrimental at the end. But put that in your mind. The additive drag, this is independent of the geometry. All aircraft, everyone, you can consider the same curve, one single curve for all aircraft existing. For all aircraft existing, for each of them, you have another CD spillage curve, and for each of them, you will have, of course, also another decol, because the decol is depending also on the geometry of the nacelle. So very complicated situation. And this situation is, in fact, problematic. Why is this situation problematic? I will explain it to you here. So, the manufacturers, they are selling their aircraft when the aircraft is not yet existing, in fact. So, a company, Boeing, Airbus, Tupolev, Embraer, I don't know, Bombardier, they will say, there is on this part of the market a niche. There is nobody flying with so many passengers over this distance. We have noticed that now everybody is going on holidays on Diego Garcia in the middle of the Indian Ocean, a very nice place to go. And so there is no aircraft on Earth that is able to do Europe-Diego Garcia. Okay. And then, so this manufacturer says, I will find the aircraft that is ideal to do that. But he will, in fact, make all the computations and already give prices, sell the aircraft even before that the aircraft has been built. So he must be able to say, the CL will be so much, the CD will be so much, the range will be so much, the TSFC will be so much, the autonomy will be so much. How can he do? How can he do something like that? You will say me, easy, I go to a wind tunnel. Wind tunnel. Okay, you go to a wind tunnel, so you have a wind tunnel, and in this wind tunnel, you put the aircraft. So you put an aircraft in the wind tunnel, so with wings, and you make testing. So you will need to make testing at different Mach numbers, because the aircraft needs to take off, needs to climb, needs to cruise, needs to land. So you will need to take different Mach numbers. You will need to change the angle of attack. The angle of attack, this is related for a given Mach number with the gross weight. So like this, you test at different Mach numbers and different gross weight. And like this, so with a certain speed that you have, you will define a certain lift and a certain drag. And so you will be able to define the CD0 and the CL. And so you will extract from there some, let's say, aerodynamic performances. Okay? Okay. But we have just seen that you need also to consider the additive drag, that you need to consider the lip suction thrust, or if you want, that you need to consider the spillage drag, and also that you need to consider the nacelle drag. We have just explained that. And you will say me, no problem, no problem. I put an engine here. I put an engine here, and I put an engine there. Is it enough? You will say, yes, I will measure like this the influence of the nacelle, because in the CD0, I will have the D nacelle that is present there. Okay, certainly if you are very, let's say, clever, you will be able to do it without the engine, and then with the engine, you will have the D nacelle, and you will be able to check the coherence. But you still have this. And to measure this, you need to have a mass flow rate in the engine. Otherwise, you will not have the shape of the flow that is corresponding to what you need to have. But in order to have a flow going into the engine, that is of course proportional with the reality. If the aircraft is 100 times smaller, m dot will be, let's say, 100 times smaller or so. But in order to have m dot related to the reality, you need to have an engine here that is running. You need to have an engine that is driving here. So you need to have a compressor that is driven by a turbine, and you need to have a flow. Well, not too complicated. So you inject, m dot compressed, you inject compressed air here in the combustion chamber. This compressed air will expand in the turbine, will drive the compressor, and you will have a flow ejection here. This is finished. So, like this, you will indeed consider that you have the lip suction thrust here, and you will also have the D-additive that is present in your measurement. But not only this installation will cost you a lot of money. Okay, it will be more expensive than just a maquette of a model of the aircraft without the engines, but it will not be so much, maybe. But the problem is coming. Why? Because this is independent of that. This is something that has nothing to see. You can fly at MA, at M1, M.1, M.2, M.3, M.5, and at another Mach number also a lot of different M dots. So what are you doing with this? Instead of testing at different Mach numbers and spending, let's say, 1 day in order to take an idea, or 1 week at each Mach number, you will need to multiply that by 5, 6, 10, 15 m dot. So instead of spending 1 week at each Mach number, you will spend 10 weeks or 15 weeks, and the problem will become unsolvable. It will cost you much too much money. How are you solving a problem like that? This is a very good question. And if you are not solving that in an adequate way, the CL and the CD that you will obtain will be wrong. If you are not able to take into account the CLCD of the naked aircraft without engines, plus the knee nacelle, plus the D-additive, plus the lip suction thrust, depending on m dot and the Mach number, you are lost. You will never have the right results. So questions, how are they solving such a problem? Okay? This is the first question. Second question, what are you trying to obtain? This is, let's say, the range. Okay? Or the endurance, or I don't know what you want to express as a global performance of the aircraft, but normally this is corresponding with a payload range diagram, which is something like that. And you want to go to fly in this point, or you want to go and fly in this point. So a certain range and a certain payload that is, of course, corresponding with a certain gross weight or a certain takeoff gross weight. And the range what is the range? In fact, this is, you can express it at least like that. This is related with the thrust you need. So this is a force derived by the fuel flow this is the mass of fuel you have divided by the fuel flow. So if you have 1 ton and you are burning 1 kilo per second, you will fly 1,000 seconds. And you multiply that by VA and you have the range. So you see that in order to go from aerodynamic performances to the range, okay, you have VA, that was already included there. You have the mass of fuel, that was somewhere included in the gross weight, but you have a big question with this. And this fuel flow is corresponding with the thrust that is equal to the drag. This is the fuel flow that is making that the thrust is sometimes higher than the drag when you accelerate, or that the thrust is equal to the drag. And this fuel flow is in fact what we call, I have erased this part of the board, this fuel flow is what we call in fact the installed fuel flow. Because this is the fuel flow corresponding to the thrust that you have on board when doing everything you need to do, not only flying, but also delivering electricity to the passengers to look at the television, delivering electricity to the pilot in order to have the avionics instruments that are working, delivering electricity to the lighting that you have on board, giving the heat to the kitchen in order to serve the people hot meals, etc., etc. And so we need to understand exactly, this is the, let's say, second problem we have, what is the difference between installed fuel flow, installed thrust, installed performances with regard to the fuel flow that was the non-installed one. And this is, in fact, a key problem. And the manufacturer that is proposing, Airbus, Boeing, Embraer, that is proposing an aircraft flying in this point of the payload range diagram, has made this full exercise. He has made wind tunnel testing, taking into account the problem you have of different mass flow rate of air going through the engines at all Mach numbers, big question mark. I have not yet explained how it is solved. I have just explained that he needs to do that. And also, he needs to look at all effects that will lead to the fact that the fuel flow is higher in flight than what he was thinking. Because he needs to deliver electricity to the passengers, because he needs to deliver